You may notice something a little different about today's live stream. I've been playing with fancy tools, try to increase the quality of my live stream, but don't expect better quality of content, because yeah, so welcome back to Machine Design. It's a lovely Monday morning with a high chance of having to cover material I forgot to cover last week. Yeah, because that happened. Last week I was like, hey, let's talk about degrees of freedom. Yeah, I looked at my schedule. I might have covered a few things that weren't supposed to be covered for a while, but I got excited. It was like, yay! Bam, bam, bam! Yes, I got a thing that pops up now. In any case, I have to go back and cover degrees of freedom because I gave a really poor explanation of it last week. And you have a quiz question on it this week, so I really need to jump back in here. So when it comes to degrees of freedom, the way that the text described it when I had you do the reading is that there are effectively the number of actuators needed to... Doing this with my hands because it makes me think, right? Think. Wheels, hands, wheel hands. Fully power the system. Okay? What I usually like to think of it is the degrees of freedom is the number of independent motions that a system can make. I kind of described it to you last week as I can reach at an object like this, and my hand can be in this position, but my arm can also be in this position, this position, this position, this position. If we fix my elbow rotation in this direction, then I still have the ability to flex it downward and upward and move my shoulder forward and backward, and I can fix my hand in one location, but I still have a number of independent motions that my arm can do to still reach that same position. And it turns out your body really likes that, which is why a lot of exoskeleton systems are so terribly uncomfortable, is because it gives you 6 axes of freedom for your hand, but this has 1 degree of freedom, 1 degree of freedom joint, or a 3 degree of freedom joint that doesn't allow your shoulder to actually move forward, whereas my shoulders like to move forward, backward, up, and down. This clavicle bone here is moving constantly. So one way to look at the degrees of freedom is the number of actuators needed, but again, I like to think of it as the number of independent motions of a system. So if we're looking at just a single component, okay, let's take a single component, the simplest that we can possibly come up with. We're going to have a square rod that goes into a square hole. Okay? And this component has some finite thickness. By the way, this is peak 3D drawing for me. So when I get done with this, I'm going to go become an artist. Okay, so we got this component that has the ability to move in and out. It's a square peg in a square hole. If we were to grab onto this component and apply it and So let's say it can move in one direction. We'll say this is the X, Z, Y axes. Okay, so it can move in the X axis. If we were to go on this end and apply an MZZ moment to it, is this connection going to transfer that moment from this component to the next one? Or are we going to have to apply a counter moment on the other end in order to keep the system from moving? Okay? Looking at that, this has everything to do with degrees of freedom. This is a 1 degree of freedom joint. Okay? This allows movement in the X, and this inhibits or constrains movement in the Y direction, Z direction, RX, RY, and RZ. Okay, so it's a 1 degree of freedom joint, which means it constrains in 5 different degrees. I can't rotate inside of this joint. I can't move it in the Y axis or the Z axis. I can't lift it up. I can't pull it around. It is very fixed in there. I can only slide it in and slide it out. Okay, I can't twist it. I can't rotate it. I can't do any of this. So a 1 degree of freedom joint, if I were to apply a moment in the Z direction, the issue is I would need a Z directional moment here, because if you think about it, if it can't move and it can't rotate about the Z axis, and then what that means is that there cannot be any Z axis accelerations. The net moments on the system has to be equal to 0. These constraints become boundary conditions. And if you remember correctly, boundary conditions are conditions that arise when you have an inability to move. They're forces that prevent motion in some directions. So as we're looking at this system, I can apply an MZZ here. I do not have to apply an MZZ here, because inside of this joint, it will resist any rotation in the Z direction. That is what the joint does. So as we're looking at joints, we're really looking at degrees of freedom here, because degrees of freedom tell you where forces are being transmitted. If you have too many degrees of freedom, you end up having the ability, you don't have as many forces that are being transmitted through a joint. In some ways, that makes the joint stronger. Okay? We'll talk about that in a bit, I guess. But when you're looking at joints, the number of degrees of freedom are inversely proportional to the number of forces that can be applied as boundary conditions. Okay, so here, if I were to, on this component, have a vertical Y-facing force, just grab onto one end and lift upward, this will resist that movement, because it has a joint. The joint exerts a boundary condition that prevents this block from moving upward, because if this block moves upward, it travels through the other component. Okay, so it's a very interesting 1 degree of freedom joint, very simple, but the concept is understanding the degrees of freedom allows us to understand what the loading conditions are, what the boundary forces are for each linkage, Okay? So let's do another example. What I'm going to do here is, instead of a 1 degree of freedom joint, I'm actually going to do a 2 degree of freedom joint. In this 2 degree of freedom joint, now I have a rod sticking through a circular hole. Why is this a 2 degree of freedom joint? Because as it stands right now, there is nothing preventing it from moving in and out. It can slide out. I can grab onto this and I can pull it in the X direction and it comes out. I can also rotate it about the X direction. If I apply a moment in the X direction here, MXX, if I apply a moment to this end, this is going to rotate through this component. All the way to the other side, it's going to continue to rotate indefinitely, and there's nothing that's going to stop it. If we were to take a set screw and set screw in like this, then we have a 0 degree of freedom joint, because that set screw is going to prevent it from moving this way, and it's also going to prevent it from rotating. A set screw through this component to this component creates a 0 degree of freedom joint, which is basically like fixing the two joints together. And then you're carrying a load through a set screw and whatever. Okay? But as this stands right here, this is a 2 degree of freedom joint. 2 degree of freedom. What it allows is X and Rx, and what it constrains still is Y, Z, Ry, and Rz. Okay? If I lift up on this, what it's going to do is it's going to exert a downward boundary condition force right here, because it's not going to want to pull through that component. If I rotate this in the Z direction, grab onto this, and I crank on it like this, cranking on it, okay? This is going to exert an RZ moment at that joint because it's not allowed to rotate in that direction. Similar with Ry. If I apply a moment in this direction, it would cause this end to bend outward, this end to bend outward. This is going to have to resist that motion because it cannot rotate in that direction. So we do have a 2 degree of freedom joint because it can rotate in two ways, but that's about it. Now, what we can see a similar joint when we have something like this. Say you have a square rod and you have a component that sits on the square rod like this. A slider that slides on top of it. Again, this is my best three-dimensional drawing, so this is my career as an artist right here. It's just a rectangular peg on this. This is the same problem I just drew earlier, but now this component is moving, and this component is fixed. It's the same joint. Just because you grab one and you move it, it's the same joint. This is still a 1 degree of freedom joint. Okay, once again, it allows movement in the X direction. It does not allow rotation in the X direction because it is a square or a triangle or whatever shape you want this to be that's not circular. Okay, again, if we were to have a set screw and drill into that, it would become a 0 degree of freedom joint because then that would prevent X directional movement. Okay, so each of the joints are really what dictate the degrees of freedom. The more joints you have, the more degrees of freedom you have. I'm going to go ahead and talk about a ball joint real quick. A ball joint is very similar to what you have in your shoulder. Your shoulder ends up being a ball joint that can also translate forward, backward, and up and down, thanks to the clavicle movement. But what a ball joint is you have one end that's a ball, and on the other end you have a cup, and the ball sits in the cup. Okay, and usually the cup will go pretty much all the way around the ball, so the ball can't really move. And what this ball joint represents is this is a 3 degree of freedom joint. This is a pretty common 3 degree of freedom joint. Ball joints end up reducing a lot of stress on components because you may have stress from components flexing in and out. And as we said, that creates, in a revolute joint, that creates a boundary condition where it has to resist that rotation motion. And if there's just a little bit of flexure, that joint has to try to carry that flexure. And that can cause a lot of stresses if it's not designed to be able to carry that flexure. Out of plane movements for linkages can strain joints substantially because it's causing loading in directions that those components were not intended to be loaded in. Having a ball joint, this ball joint is intended to be loaded in all directions. As a 3 degree of freedom joint, I call it a 3 degree of freedom joint because what it does is it allows Rx, Ry, and Rz. Okay? I can twist this ball. I can twist my shoulder. And that doesn't hurt anything. Okay? I can rotate my shoulder up and down. Again, doesn't hurt something. I can rotate it this axis. Doesn't hurt something. That's all 3 rotational axes. That's what makes this a 3 degree of freedom joint. Now, you grab onto my arm and try to pull it out of its socket. It resists this movement. It actually, the ball catches on the cup. So it constrains. Woo! I'm trying to spell that word right. It constrains XYZ movement. It cannot translate. It can only rotate. So a ball joint is pretty typical there. So what happens when you have multiple joints getting together? Well, let's say I have a fixed component connected to the ground, a fixed component, 0 degree of freedom joint, whatever. We'll consider it part of the ground. I put in a revolute pin, and that revolute pin goes to a slider. And this slider slides on some kind of a rail where this rail is fixed to another wall. Okay? How many degrees of freedom does this system have? Well, looking at this joint right here, this is a 1 degree of freedom joint. We're going to assume that it's like a bolt. It actually has a head on the other side that prevents movement in and out. This joint right here, this bolted joint between this link and the slider, that's a 1 degree of freedom joint. And this connection here between the slider and the rail is a 1 degree of freedom joint. So we have 3 1 degree of freedom joints. This should be able to move, right? Well, not quite. Because the issue is, if this component here rotates upward at all, this joint has to rotate upward. Okay? This line right here represents the connection between the linkages. If this component rotates upward, this axis between those two joints rotates upward, because that's what happens. It rotates with the component. When this axis rotates upward, this component travels in the y direction. However, this component back here is restricted from moving in the y direction because of the 1 degree of freedom joint on this rail. This system, as drawn right here, cannot move. It can't move. It is fully constrained. It's stuck. You try to put this in motion, it won't move. It won't do anything. You throw an actuator on here, throw a motor on here, that motor's going to burn out real quick because it's not going to do anything. It's going to... So what can we do to fix this system? Well, we have to allow this to move upward in some ways. So one way we can fix it is by, instead of taking the rail and having the rail be fixed to the wall, we can add another 1 degree of freedom joint and connect this to the wall. Now, as this component moves upward, the rail also moves upward, and this component slides along it. Okay, this is acceptable. This system now has exactly 1 degree of freedom. How do I know that? Well, there turns out there's a formula. There's a degree of freedom formula. And that degree of freedom formula comes in 2 flavors. We'll talk about the planar flavor first, because planar flavor is the more delicious of the two. Okay, so with a system like this, what you have for the whole system is you have, in a planar configuration, this is a planar movement because it doesn't travel in the z direction at all, and there's no ry, nope, or rx. It only allows for our rotation in the z. Okay, so in planar conditions, you account for x, y, and rz movements. You don't care about ry, rz, ry, rx, or z movements. This is a planar configuration because it cannot move in the z direction at all. We're assuming that. We're assuming that it can't twist in ry or rx configurations. The only way it can move is in x and y, and if it rotates about the z-axis. Okay, that's going to be our planar conditions. For planar conditions, the degree of freedom formula looks like this. 3n minus 1 minus 2h minus l. Pretty sure that's right. I might have to go adjust this. This might be the L, this might be the H. I think I'm right though. What do each of these variables mean? N is your number of linkages. H is your number of nope. I did get it wrong. Your H is your number of 1 degree of freedom joints. And your L is your number of 2 degree of freedom joints. Now you notice you won't have any 3 degree of freedom joints here, because the 3 degree of freedom joints are where there is no joint. If it allows for movement in the x, y, and rz directions, it's as if these components aren't even touching. There cannot be any power transmission from those components because there is no boundary conditions. Those two have to occur simultaneously. I'm going to change out the battery real quick in my pack because I think I'm starting to cut out. So this is the point in the lecture where I stop telling you about class stuff and I start telling you about my steamy love life. And I have a couple of so, but I'll be okay. But thank you for caring. Okay. Sorry, I'm not used to having heart-to-hearts in the middle of class, but okay. So, get yourself together, man. So what we have here is, I'm going to go ahead and take an analysis of this system according to this degree of freedom equation. And this is equal to the number of degrees of freedom of the system. Okay? So again, your system requires, for a planar system, it requires three values: the number of linkages and your joints. That's how you figure out the degrees of freedom. That's it. What are your joints like? How many linkages do you have? Degrees of freedom. So for this, how do we figure out what is and isn't linkage? Well, we kind of have to break this apart here. This piece, if we were to pull it out all by itself, has two revolute joints. That consists of two axes that it rotates about in the z direction. This is RZ, RZ. No X, no Y movements. Okay, this one is mounted to ground, or to some component that's mounted to ground with a 0 degree of freedom joint. So we're just going to consider that to be ground. Great. Now, what this bolts into is a block. This block has an RZ joint and an X joint, meaning it allows rotation in the Z direction. It can rotate about this component, and it can move in the X direction. Okay? You can consider that the rotation in the Z direction for this one may be the input. If it's connected to a motor, your RZ about this axis may be your input to the system. And this would be the input to the link and the output to the link. This would then be the input to the link, and the output would be motion in the X direction, or motion along that linkage. Okay, so this would be your input and your output. And then for this linkage here, now we have a bar that is rotating up and down. Here, this has an X degree of freedom joint that allows the movement in the X direction. And then over here, it has an RZ joint. And then on this backside, we have ground. Okay, so how many linkages are we dealing with here? Well, this is 1, 2, 3, 4. This is a 4 linkage system. Yes, we are counting the ground. Now we're going to actually assume that these two ground ends are connected. Anytime you have something connected to ground where two ends will not move relative to each other, but will move as a pair, you can assume that they're connected and that they are one component. So even though, yes, there are two grounds in this system, we're going to assume that they're connected somehow. And they probably are. If they're moving, if they're connected such that they cannot move relative to each other, they are connected somehow with some kind of rigid system, so they end up forming one single component. They move as one rigid body. Okay? So we have 4 linkages in this system. Yay! Now the number of degrees of freedom that we have. Well, let's see. We have number of 1 degree of freedom joints. Okay? This allows RZ, this allows RZ, this is RZ, X, X, RZ. We only have 1 degree of freedom joints in the system. And we have 1, 2, 3, 4. So the number of 1 degree of freedom joints is equal to 4. Number of 2 degree of freedom joints is equal to 0. So according to this equation, your DOF is equal to 3 times n minus 1 minus 2L minus H, where n is now 4. So this is equal to 3 times 3 minus oh man, I know I got this backwards. I totally got this backwards. Yep. Wow. Okay. Fantastic. I was right the first time. And then I second guessed myself. H is number of 1 degree of freedom joints. This is 2, yeah, that stays the same, just H and L are flipped. H, L, so now we have 2 times, we have 4. So this becomes 9 minus 8, and this equals 1 degree of freedom, which is what I told you at the beginning. Okay? So the number of 1 degree of freedom joints here are really what allow this to move. If we transitioned any one of these into a 2 degree of freedom system, where say this instead of a pin joint is now a slot joint, so it allows rotation but also movement in this direction, now we run into an issue. Because now this, being a 2 degree of freedom joint, being a slot joint, we would need 2 independent actuators. So if we put, excuse me, if we put a motor on this linkage, it would cause this to rotate, but without having a motor to dictate how far into this slot this component was, we would never be able to fully define the system. It would bounce around a lot until the thing hit the edges of the slot. If it never hits the edges of the slot, this component would rotate, this component would lift, but it wouldn't even slide on the member. That's it. Just lift. And it could slide on the member if you wanted it to, but it wouldn't define anything. So changing this system by adding another degree of freedom in the joint, now if you go back through the math with this now being a slot joint, it becomes 3 times 3 minus 2 times 3, because now there's 3 1 degree of freedom joints, and then 2 degree of freedom joint becomes 9 minus 6 minus 1 equals 7, which means you have, equals 2, because I can do math. You have 2 degrees of freedom in your system, which here means the number of actuators that would be needed to fully define the system, but it's also the number of independent motions of the system. You can move things without other things moving. Okay? Without any power being transmitted in the X direction here. So that's one example of a planar degree of freedom system. Okay? Now what we're going to cover is you can do this for 4-bar systems, 4-bar linkages, have 1 degree of freedom total. Always do. You can come up with 5 and 6-bar configurations that do have 1 degree of freedom. Again, the benefit of a 4-bar system is that it has 1 degree of freedom, which means you have 1 motor actuator and you're able to control the output based on 1 motor actuator. So that is one of the nice things about having a 4-bar system, is that it does have that 1 actuator type output system. Okay? But what happens if we're dealing with a non-planar system? What happens when we're trying to transmit power where some of our joints may allow rotation in the Y direction or rotation in the X direction or even movement in the Z direction? What happens to the more complex systems or systems that have ball joints in them? Okay, there's a different degree of freedom equation that you use. The degree of freedom equation is equal to this: 6n minus 1 minus 5. And what we have to do here is specify this as J1 for J2 minus 3, J3 minus 2, J4 minus J5. Okay? And what this is these are joints with 1 degree of freedom. This is joints with 2 degrees of freedom. Joints with 3 degrees of freedom. Okay? And we have to continue to do this. This is the equation for general 3D motion. And you'll notice that for a 4-bar linkage, if we were to do this, 4-bar linkages are comprised of only 1 degree of freedom joints. So what you have is 6 times 4 minus 1 minus 5 times, let's see, in a 4-bar linkage you've got 1, 2, 3, 4. I probably could have counted that in my head. Okay, so you got this. This ends up being 18 minus 20 is equal to negative 2. This is one of the very interesting things about planar mechanisms. Okay, technically, this system isn't supposed to move, according to this equation. But what this negative 2 represents is what's called over-constrained. Okay? A 1 degree of freedom system, like a 4-bar linkage, which, ignore what I'm talking about right now, is what's called perfectly constrained. It is a well-constrained system. Oh, nope, sorry. Systems with 1 degree of freedom, or maybe 2 if you're intending to have 2 actuators, or 3 if you're intending to have 3 actuators. The systems with the same number of actuators as you intend to have degrees of freedom are called well-constrained. If you have more degrees of freedom than actuators, then you've got some independent movements in there. It's moving around in ways you cannot control or predict. This is an under-constrained system. If you have more actuators than degrees of freedom, then this is called over-constrained. In this system, we have 1 actuator, and we have negative 2 degrees of freedom. So this is considered over-constrained. In an over-constrained system, what it means is we could eliminate some of our constraints to make the system better. One of the ways to do that is with this system, you have 2 different joints. All of these joints only allow rotation in the z direction, which is great, but that means you're carrying Rx, Ry loads, and Z loads through both pins, which is kind of unnecessary. You only need 1 pin to carry it. If you were to replace this joint and allow Rx, Rz, Ry, and Rx rotation, turning this into a ball joint, that does change your general equation overall. And it also means that all of those forces are going through only 1 pin. And you know, if you want to design this to handle that, great. If you want to leave this as a planar linkage, that actually doesn't cause problems. Even though in the general 3D equation, this 4-bar linkage has negative 2 degrees of freedom, those 2 degrees of freedom are being taken out in the other directions. So I'm going to go ahead and replace one of these joints with one of those joints. And the new equation comes out to be 6 times n minus 1, so that's 4 minus 1 minus 5 times 3 minus 3 times 1. The new equation for this now is 18 minus 18, and your new degrees of freedom is actually 0. Huzzah! I'm going to do one more thing. Not only am I going to make this a ball joint, I'm going to make it a sliding ball joint that allows movement in the z direction. I can do that. And when we do that, it does not cause this system to move any differently. But it does allow for some shifting in the z direction. It doesn't cause any major loading in the z direction. When that happens, this now becomes a 4 degree of freedom joint because it got 4 different degrees of freedom that it allows. And this now finally has 1 degree of freedom, which is what it is. You can't actually do any more modifications to this system. What I'm doing here by adding these degrees of freedom to the system is I'm doing something called reducing redundancy. In linkages, redundancy refers to any time when you have multiple constraints acting on a system and prevent movement in a certain direction where those multiple movements are unnecessary. Redundancy is a major issue in machine design. Theoretically, redundancy doesn't exist because we can draw linkages where they're multiply nicely constrained, etc. But the issue is, in reality, having multiple constraints on the same component can cause dramatic issues. If these two axles are out of line, the connection point here is here, if we're looking at it from this way, the connection point here is like this. Like this. This could cause the entire system to freeze just by having these two connection points out of plane with each other. Reducing this redundancy actually makes the machine move smoother. Now you can, just if you make sure that these are in plane, the 4-bar linkage ends up working just fine. Planar linkages are kind of the exception to this redundancy rule in that it's okay to have redundancy in the R, Y, R, X, and Z directions as long as the entire plane, the mechanism, is moving in one plane. So redundancy is only, but you can figure out a way to do that in other places too. So this is just kind of an introduction to degrees of freedom, calculations that go behind it, how to figure out how much degrees of freedom you have. Your mechanism you're designing for your robotic leg should have anywhere from 1 to 2 degrees of freedom. You are required to put a spring in your system. Having a spring in your system means that it compresses, and that is 1 degree of freedom, but also as it lifts or moves upward, that is a 2nd degree of freedom. So you will be designing probably a 2 degree of freedom system where one of those degrees of freedom is limited, not constrained, but limited by a spring passive component. Okay, and if you have questions over that, we will be talking about that in class because we're going to be working on that this week. We are not going to have an example over shaft design in class, so I'm probably going to have a 3rd video this week. I know I promised that last week and I never did, but we'll have a 3rd video this week talking about shaft design and giving an example there. But today I just want to get through fundamentals of what shaft design is. Tune in for my next lecture, which I'm about to have. We're going to cover shaft design right now, okay?